Okay, hello everyone. Welcome to the meeting of the 6LO working group. Please make sure that you are in the right room. My name is Carlos Gomez. The other chair is Shweta Bandari. She is remote today. And our responsible AD is Eric Klein. Hopefully he will arrive anytime soon. So we will need some minute takers. So is there anyone who would like to volunteer as minute taker? Recall that we don't need to have everything that's being said written. We just need like the main decisions, main outcomes, main action points. By the way, this could be for either in-person participants or remote participants. Anyone would like to do so? Okay, well, if there's no volunteers, well, we'll try to do that by ourselves, but please try to join and contribute to the process of taking minutes that I'll explain right next. So on the slide, you can also find a pointer to the online agenda, which you may have seen already several times at this point of the week, and also a link to the HedgeDoc, which is the tool that we are going to use today for taking minutes. Recall that this is a collaborative process, so everyone feel free to join and contribute to the process of taking minutes. So similar to the last few IETF meetings, there are also some meeting tips for this one. Recall for in-person participants, please make sure to sign into the session by using Meetecho, such as by using the on-site tool that you can find from the data tracker agenda. And remember that you need to use Meetecho to join the queue. There's a single unified queue, which is managed from Meetecho. And also blue sheets are automatically generated from Meetecho. Also for remote participants, please keep your audio and video off unless you are presenting something or talking. This is the Notewell. This is a reminder of IETF policies, which are in effect on various important topics, such as patents or code of conduct. So please make sure that you have read it. And this is the agenda proposed for today. The first presentation is the usual chair's introduction, which is currently in progress. That will be followed by a presentation on the update of the 6LO use cases draft by Yonggeun Hong. And that will be followed by a set of two presentations by Luigi Iannone on the topic of path-aware semantic addressing, PASA. The first one is the base document for PASA, path-aware semantic addressing for LLMs, and the second one is a companion document which focuses on the reliability considerations of PASA. Finally, there will be one other presentation given by myself on the transmission of SHIC compressed packets over 15.4 networks. So as you can see, this time the agenda is a bit less packed than as usual. That's partly, well, Pascal is here remotely, but unfortunately he wasn't able to attend in person. So today he will not be presenting his drafts. However, he is attending and hopefully will be able to contribute to the discussions. And the point is that today we have a bit more time. So perhaps we can use this time for more discussion if needed. Other than that, is there any comment, any objection to the agenda? Okay, so if there's no comments on the agenda, now let's move to the report on the working group documents status. The first document is that, well, actually, since the last IETF, we have this new RFC 9354 on IPv6 over PLC. Congratulations to the authors and many thanks to everyone who has contributed in the process in the form of comments, reviews, and so on. So again, congratulations and many thanks to everyone. Also, the next document provides also some good news. This is IPv6 over NFC. It's now in the RFC editor queue. So you may recall that quite some work has been needed to reach this stage, but now the document will hopefully be published anytime soon. Then the next document is the 6LO use cases draft. Here the document was evaluated by the ISG. Then the authors recently updated the draft in order to address the comments. And then the last discussed ballot was cleared recently. And there will be a presentation later today. Apparently, there's still a very minor comment that will be addressed, but hopefully there will be -16 published soon. So later today, there will be a presentation on the last set of updates in the 6LO use cases draft. Then the next document is the IPv6 ND multicast address listener registration. This document is pending the Shepherd write-up, so we hope that we can get it soon. And since the last IETF, there are two new working group documents. One is path-aware semantic addressing for LLNs, and the other one is the transmission of SHIC compress packets over IEEE 802.15.4 networks. By the way, these two will be presented also later today. Any comment, question? Okay, so if there are no comments, then we can move to the next presentation, which will be on the update of the 6LO use cases draft.
Okay. Good morning. My name is Yonggun Hong. I'm working for Daejeon University. So nice to meet you again. I present the update of the 6LO use case draft. Next page, please. Yeah, this is the history and status. So the last year, the December, I got the comment from the ISG last call. So this the 15 version. I try to resolve the comment from the ISG. Okay, next page, please. So I got 9 or 10% the comment. The first one is the transport area director. So his comment was 2. In our draft, we in the table we use the low, moderate, frequent, infrequent expression, but he says that if we refer other document, then it's more better. So I searched the document. So I found the one relevant document, RFC 8578. So I, based on that RFC document, I changed low, moderate, high, that the yes expression, and the no is no expression. And he replaced 4G LTE to cellular. Okay, next page, please. The other comment come from the area art area directors. So it's very simple. The move RFC area 2002 into normative section and add the full name of the OFDM, orthogonal frequency, blah blah. Yes. Next page, please. And the third comment is come from the security area director Paul Winters. So it's kind of many is the comment come from here. So in the main body, we have the security and encryption section. So he suggests to change the paragraph. So based on his command, we update the paragraph. And he want to add some EDHOC as one of example. So I add as a reference. Next page, please. And he found some no reference in the BLE, DECT, NFC, PLC. So add a reference of each of them, and we remove some the reference of the specific IETF working group, for example, 6LO, 6LO, etc. And I separated a normative and informative the reference. Next page, please. Yes, this comment come from the Roman Torvip, is the security area director, is many. So also he has some comment for the regarding security and encryption section. So I update the paragraph to resolve his comment. And in our draft, we use the low cost expression. So he has some concern about their usage. So I delete the low cost expression. Next page, please. And another, the comment is kind of the minor. So I updated as he comment. Next page, please. It is the same situation. It's a very minor comment. Okay, next page. And yeah, this is comment come from the Ralph Eggers, general area directors. So his comment is kind of the minor comment. Update the IEEE area 15.4 reference. So I update, and he suggests some the change the expression. For example, traditional to classical and native to fundamental. So I update as his comment. And I added the update the NFC. The existing version is 18, so the latest version is 22. So I update as like this. Next page, please. Yes, this is the same comment from the Ralph Eggers. It is a minor comment, so I updated as the full to resolve his comment. Next page, please. Yes, this is comment from Eric. Oh, sorry, sorry, it's my mistake. So yes, his comment is kind of the reasonable and kind of the minor. So I updated as his comment. Okay, next page, please. Yes, it's the same situation is kind of the minor, and I update as his comment. Next page, please. Yes, this comment come from the Carlos and the Robert Sparks, so it's kind of minor. So I updated as he suggested. Okay, next page, please. So as you can see, the update is a kind of the minor, was some typo. So I found that one thing is missing. So the Robert Sparks pointed that. So I changed this, the NFC use case from healthcare service to the secure transfer. So I changed that in the main body, but I forgot in the table. So in the 6th version, I changed that as a small point. Okay, next page, please. Yes, that's all. So if you have any question or comment, so let me know.
Eric Klein, thank you for all of the work. Yeah, so I was actually getting ready to advance this to the RFC editor on draft 15.
Yeah.
I just had another, this document was not contentious, so I had another more contentious document I was focusing on. But I guess it's maybe good that somebody found this, and it looks like -16 is ready to go, will be ready to go to the RFC editor.
Yeah.
Perfect. Thank you so much.
Thank you. Okay, thank you.
Okay, thank you. Okay, hello. So yeah, the next two presentations will be on the topic of PASA, path-aware semantic addressing. So Luigi will be the presenter.
Yes, I ask it to share.
Yeah.
So that I control it.
I'm not getting. I'm not
Nothing?
getting them. Usually I should see a request.
Yes. Let me reload the page.
Otherwise I can pass them for you if you want.
Let's try one last one.
Sure.
Nothing. Okay.
No.
You can share for me, please.
Okay, sure.
Okay. Good morning, everyone. So this is an update on the main spec of the PASA document, so path-aware semantic addressing, which has been recently adopted. Slide. So we first had a revision in December. If you remember during the last meeting, I said we did good progress, but there are still a few things to be fixed, which we did. Okay, next. So, it's a weird animation. I'm not good at animation. Next. Okay, version 01 that was submitted in December, then went through the working group adoption call. Early February has been adopted, so we submitted early March revision with the new naming and few polishing. Next. So the changes in a nutshell. So from a technical perspective, we simplified the routing header format. Okay, we simplified the communication with the destination outside the PASA domain, which actually was the thing that I said we still need some work on. And we realized we can further simplify the address configuration, and we'll go over it. Some polishing. Now, at some point during the discussion to prepare the 01 document in December and afterwards during the call for adoption, the co-authors realized that at the end of the day, the document as it is today is really kind of just an extension of the 6LO mechanism. So the initial intended status of the document was experimental. We submit that now as a standard track, but this is up to the working group if anybody has a different thinks that is not appropriate or any comments to say.
So as Carlos well knows, in the Shepherd write-up, there will be a section about please describe the implementations, how many there are, and whether they interoperate, and so on and so forth. So I don't know if you have anything you want to say about that. I actually haven't checked to this document. It might actually have an implementation section in the appendix.
No, it's ongoing, so it's not something deployed, let's say.
Okay.
Especially we need to code the last modification. Okay. Slide, please. The first thing is that we simplified the header content. This is the header as it was before. If you look at the first line, there was a address type because we felt that we need to understand encode whether or not the destination is inside the PASA domain or not. We realized this is not necessary. So slide. Yep. And this is actually the new header in the sense that now the size previously was counting pairs of octets, so the quads, okay? This is not necessary anymore, so just we count the length of the address in octets. The address type is not needed anymore, so we have 2 bits that reserved us for future use, okay? Slide. The reason why we can simplify the header format is because actually if we realize that the destination is outside the parser domain, we actually don't need the 6LO routing header, parser routing header at all. We don't need it. We just need to do IP in IP, follow RFC 8138, use the default route, which is just the parent of each node, okay, until we reach the gateway, and then we send out. So there is nothing really specific to be done. We don't need to do the parser encapsulation in case the destination is outside the parser domain, okay. Next. Now, for the others configuration, the idea was we shifted it a little bit, and now using 8505, so the extended address registration option. Now, what happens is usually you check where you can register, then you register your link local address. Now, there are a few reserved bits in that packet. Okay, the idea is to use 2 of them. One is the parser bit and the other is the host bit, because if you remember, the nodes in a parser domain have 2 roles. Either is a parser router or a parser host, which basically a host is a host. It's not forwarding packets. So in the tree that we build is a leaf, basically. Okay, parser router, just nodes in the middle that do forward packets in a stateless manner, but still they do it. So we need to know this role. Okay, so basically with these 2 bits, what happens is that we are signaling that we would like to obtain a parser address, and we say which role are we playing. Okay, next. Pascal?
Hear me okay?
Hello, we can hear you, but a bit low.
I'm sorry. I wanted to just point out that those bits are rare and precious. So we'd have to think if we really want them. So because there is competition with multiple drafts which are pending, which also require those bits. So let's discuss that.
So your voice comes out really chopped. Understand there are other drafts related to the bits. Maybe you mean some synchronization to be done. Actually, we don't use the same bits.
Let's consider that. Yes, there are very few bits.
Sure.
That's what I'm talking about.
Yeah, sure. I mean, at this point, we still can move the bits if that's the comment.
Yeah, by the way, so I understand that this draft will update RFC 8505.
Yeah. Right.
Okay.
Thanks. Okay. Next. No, Kiran.
Sorry, I just as a suggestion that you're using a toggle bit host and router to describe whether it is set or not. Can you increase it to 2 bits so that explicitly host and forwarders are set? I mean, I'm more comfortable if you explicitly tell whether this is a host or a forwarder. I don't want to use the default mechanism. Like you want to explicitly set the bits.
Yeah, exactly. I mean, the declaring the role was something that was there from the beginning. It's just that it was signaled in a different way. So now we need.
Yeah, what I'm saying is that instead of using just 1 bit, use 2 bits.
For the role?
Yeah. so that end user is explicitly setting that I'm asking for host or forwarder rather than not doing anything in case of forwarder. I mean, default assuming that it is a forwarder if it is set to
You
0.
mean 1 bit host, 1 bit
Mhm.
forwarder, and
Yeah, something like that. It also helps us give some expansion that if I want to have some notion of root, like in duplicate reliability topology, if I want to give some indication of roots, it will be useful.
okay.
Just a suggestion. I think we
We can
talk
discuss
about
more.
it.
I mean,
Yeah.
let's take it to the list. I'm not against. I didn't think about it, to be honest. Okay. So how it works with this others configuration procedure right now. So the node boots sends the multicast router solicitation, and based on the on the router advertisements that he receives, it selects one parent. Okay. First come, first served. Anything can work. Just select one. Okay, and at that point, the node send a neighbor solicitation with the option, okay, to register the link local address. And in that message, you put the P bit and the H bit. So you set the P bit, I want a pass address, and the H bit accordingly, right? Whether you are a host or a router. So if everything works well, so the parent will send back a neighbor advertisement with the option, the status success, the 2 bits will be sent back unchanged, okay? But there will be the proposed pass address appended to the returning message. So we have the link local address, and then we have the proposed pass address, okay? As you can see here in the slides. Now, the procedure didn't finish yet. What we do is next, the child must register the pass address. So because the parent is proposing an address, the child will register using just full 8505, okay? And this basically will signal that the child node has accepted that address, and the parent confirms that yes, please use it. Okay, so this is simpler than the previous solution that we have in the document. Next. So the core of the document, the mechanism is pretty stable. Yes, we updated and simplified a few things here and there, which is actually pretty nice because even more, the solution is even more embedded in the 6LO framework, let's say. What we need to do, high priority is the security section. I mean, this has been, the comment has been raised during the call for adoption. The security section is, let's say, empty. But yeah, we will work on that and propose a security analysis. Yeah, and I think that's it. Even if you do next, there is a thanks maybe. Carlos, please.
Yeah, so perhaps about possible gaps. Yeah, the security one is clear. Then perhaps maybe the topic of multicast, how you deal with multicast in the document could be something else to look at.
You're right. You're right. We don't say anything about it. You're right.
Okay.
Noted. Good point. Anything else? Or we switch to the next? Same topic, different angle. So this second one is just specific to reliability consideration. This was a concern raised 1 year ago, I mean, something like that. And we thought, yeah, we need to have something specific to cover the reliability part. Okay, next. We had there was a change of name at some point, and we have a revision submitted early March. Okay, next. The main content structure didn't change that much. I mean, what we did 1 year ago is to introduce the context, the problem statement, what we consider are the two solution alternatives that we have, considerations about failure detection and recovery, and considerations about resiliency. What we did since the last meeting is rewriting for clarification. There are various pieces that were unclear. We fix a couple of bugs in the examples, especially in the first part of the document. The numbering that we were using was not consistent, and we did align the text with the main specs, okay, with the different modifications that we had. Next. In previous meetings, I never had really the time to go over this document. Today we have a little bit of time, so I will go a little bit slower on the things. So there are some prerequisites that we need in order to discuss about resiliency, reliability in PASA. So we do need redundant links, because otherwise we cannot guarantee redundancy, okay? Resiliency. Some may not be actively used, so it depends on the solution. You can have active or active passive. It remains the fact that when we use the active links, our topology is a tree, okay? And all the nodes need to have a secondary parent, okay, to have alternative path, okay? This is except the root node, because at that point, we are outside the PASA domain. There are all the things that apply in order to guarantee reliability, okay? The alternative parent usually is connected through a link that is not actively used. So in having this, now is how do I use the secondary parent, let's say, or alternative parents, in order to guarantee reliability? So you have two different basic approaches. Either you use multiple addresses, so basically you generate several topologies, alternative topologies, and you then select one or the other depending on the situation that you have. Or you still keep one single addressing space, but you include further information on each and every node on who is the alternative parent, who is the alternative child, and this is everything in one domain. The multi-address domain, you have additional information, but they are logically separated in a certain way. Next. This is an example of the multi-address solution, okay? The different circles are the nodes, and this is an example of how we can build the primary topology, okay? In red, there are the addresses that we can build with the main specs, okay? The document that just presented. Next. So the red dot and the green dot are the two alternative routes, okay? And then the green, we have a secondary topology built in a different way. So as you can see, the addresses are different, okay? Because we built differently, okay? Next. And this is the vision if you overlap the two topologies, okay? Each and every node has two addresses, okay? The red one and the green one. So you can use one or the other. Now, usually in a normal case, what you do is you have your primary topology and use that one to communicate, okay? And the only thing is when something happens, somewhere you have to create state that, look, there is a failure. Please switch on the secondary topology. By the way, I use just 2 topologies. Nothing prevents, in principle, to use even more topologies. But, I mean, this is obviously a trade-off. Please, go ahead, slide. So this is just an example if one of the links fails for whatever reason. Next. So what we can do is that downstream to from the failure, you can somehow signal to through the secondary topology to the root. Look, to me this link failed. Okay. So if you want to reach anything that is rooted from me, that any subtree, okay, you should tunnel the traffic to me using the secondary address. So basically, if we look at the primary topology, the red address is 100. So 100 is signaling I have an upstream link failure. Please tunnel all the traffic to me through the secondary topology, which has using as a destination address my green address 0101. Okay, then I can decapsulate and send to all my childs. Okay, so the root has to install a rule that says if the destination prefix starts with 100, encap and go through the secondary topology. Next. Now, upstream with respect to the failure, we need to do something as well. Usually you can use a message, an OP-IOP message to signal upstream, look, the downlink to 100 is broken. Okay. This is not the case in this example, but this is necessary if between the node with the red address 10 and the root, there were other nodes. So this message going upwards, op by op, signals to those nodes. If you go to 100, actually redirect to the root, okay, which then will forward on the secondary topology. Next. Now, as a kind of optimization that you can do is you may consider, and 100 may consider to signal to all of these his childs, consider using directly your secondary addresses, because on the primary topology there is a link failure. But I mean, this could be optional just to optimize things in a certain way. Next. This is just an example of what happens if 2 nodes wants to communicate. I put the blue box around. So if we want to send a packet from 11 to 1001, so this is the red address. 11 is the node close to the root, and 1001 is the leaf on bottom left side. Okay. What happens is that when 11 sends the packet, he sends it to the root. This is a usual parser because the destinations start with 10. It's not the same prefix. Then it reaches the root. There should be there a redirect rule. Okay, so the primary root 1 will encapsulate toward 0101, which is the secondary address of the node, which is just downstream the failed link. Okay. So with this encapsulation, what happens if we shift the packet to the secondary topology, rooted in 01, and we use parser forwarding as for the other document. And in this way, the packet will statelessly forwarded to the node 100 or 0101 on the secondary tree, decapsulate, and 100 will send to the final address. The other way around, what happens is that 1001 will send up to 100, okay? We are using the default gateway, the default route, okay? So we just send upwards. Yeah. No, that's wrong. This is, we send outside, but we send up. 100 says, oh, the uplink is broken, so I send through the secondary topology. Okay, so again, I can encapsulate, send up, goes up, and to 1, the encapsulate says, oh, this is internal, I send it downward using the PASA specification as usual, so the destination is reached, is 1-1. Okay, I hope this is clear. If you have any question. Okay. Even offline, huh? Don't worry. Rock.
Hi, Guangpeng Li from Huawei. Just the 2 comments here for the reliability of PASA. The comment 1 is about reliability. I think the reliability part should be additional feature of PASA. And it should depend on the redundancy conditions. For example, redundant link or redundant nodes. This is comment 1. For comment 2 here is about whether to use multiple addresses mechanism should depend on limit of applications, because some applications cannot work with multiple addresses at all. So if we want to use ID instead of address, it may be an option, but I think it's another story here. Thank you.
So the first is again, there is a general comment, which is like the prerequisite that we need in order to have a reliability, which we may agree. So on the use of multiple addresses by an application, you have to make the distinction between application and node. You can have multiple addresses on an interface. Is IPv6, I mean. The fact that the application cannot switch between 2 addresses because there is already a connection set up, this we know is an issue, okay, which can be solved on the upper layers, can be solved on with other solution. It's not up to us to solve that problem. I mean, can you go back one? Here, that is why the fact that we signal downwards, if please consider using your secondary address, is just a hint. If you can, do it. If you cannot, we will redirect. I mean,
yes,
but you don't need to change the application. You don't need that.
Yes, we don't want to change applications, but it depends on the application type. So I think we need more discussion in the future, maybe on the list, and we need more input from the community.
This is input from the community is on all the document, including that part, certainly.
Yeah. Thank you.
Okay, thanks. Slide. Okay, slide. I will skip this. It's just the flow chart of the operation. It's just so basically, in the main spec we have the flow chart that says how we do stateless forwarding. Here there are a couple of boxes more that just say, is there a redirect rule? Yes, redirect. No, do PASA. Basically, is this. Next. Rock, you are still in the queue. You have further comments? I guess not. So the alternative solution is to have one single PASA domain using one single addressing space. Okay. The idea is you locally store alternative parents and children. In a certain way, is the same thing is the sense that you add state, okay, to each node. Previously was an alternative topology, which is locally separated. Here, everything is together and you explicitly mark, this is alternative, this is alternative. Slide. Okay. And this is an example of what you can have in the, let's say, neighbor cache. Basically, you have the address of the current node, the primary parent, primary forwarder child, leaf. There is still some refinement to be done with the some NSA relic. Anyway, so basically what we do is we clearly mark who is the primary parent and who are the primary children. Okay, and then we add all other neighbors that could be alternative, upwards as parent or downwards as alternative children can be used to forward. Okay, so we have an enlarged table. Slide. So if, like in the previous case, we have a link failure, so something that we throw away from our table, and now we need to signal this to the root. Okay, so as previously, we have the node 10 that sent something upwards and say, oh, the link to 100 is broken. Okay, what happens is this trigger some calculation on the root. The idea is to try to find an alternative path. Okay, slide. So in order to find the alternative path, actually the root has to have a full vision of the topology. Okay, so which may trigger some more messaging when you do your addressing and you set up the network. Okay, so the idea is then if we have a communication inside the PASA domain, like previously we have the two blue box, and we go from the 1101, which is the box on the right, the node on the right, to 1001, the box on the left. 1101 sends the packet to the root, use normal stateless password forwarding because they are not on the same prefix, on the same branch of the tree, right? Root 1 should have computed already an alternative path. Okay, in this example, we go from the root 1 to 110, okay, to 100, then to 1001. Okay. Now, because we cannot follow this path using PASA directly, we need to do something else. Could be something like segment routing. Okay, we didn't go in any details of this kind of solution to enforce the path. Okay, we just explored the possibility at this point. Okay, but certainly we need a mechanism in order to enforce the path. On the way back, what happens is that 1001, okay, sends to node 100, it's passed using normal forwarding. Because the link failed, then what happens is that no 100 can send the packet upwards to an alternative parent. Okay, now the nice thing is that at that point nothing more needs to be done, in the sense that we can follow the normal PASA stateless forwarding. Okay, because each node looks at the destination address and can make a decision. In this case, 100 can decide, oh, I send to the alternative parent 110. Okay, when the packet is there, 110 checks the destination address and then say, oh, it's 1101. So if it's one of my children, okay, so I can send the parent directly. I don't need all the time to go up to the root and down, okay? Just use normal PASA forwarding, which is, I think, is a nice feature for this kind of solution, okay? Next. Okay, same thing here. We augmented the flow chart in order to show what needs to be done additionally in order to do the forwarding. Next. So this is very, very simple table in order to compare a little bit the two solutions. Okay, in the case of multiple addresses, the state that you keep in the root is low because you just have redirecting rules, okay? So assuming that you don't have a lot of failures, you have few rules, okay? Same thing in the forwarders, okay? However, because you have limited knowledge, the root is not a full vision of the topology, reliability may be lower compared to the single address solution, okay? However, I mean, if you have a lot of link failures, you have a bigger problem in there, not the state of a single node. Anyway, in the single address case, the root state is higher because, as I said, the root needs to have a full vision of the topology in case of failure to calculate an alternative path, okay? Forward state is low like the multiple addresses, just logically one single table, basically, okay? But on the robustness part, because the root has this full vision, we can handle maybe multiple failures in more optimal way, okay? Next. Okay. I hope I was sufficiently clear. As usual, any contribution, any comments is very, very welcome. We still need some work to do. We need to refine the wording. There are a few parts that I'm not satisfied about the clarity, okay? As I also noticed in this slide, there is still some NSA terminology relic. One important thing to do is to align the examples, because actually if you go to the draft, the example that is provided for the multiple addresses and the example that is provided for the single address solution are not the same. So it would be nice to have the same example, exactly the same example, so that we can really compare what is happening there. And security is still ongoing as for the main spec anyway. Yeah, all in all, what I want to say is just we need some more work on this. I'm not totally satisfied on the clarity of this document, but we will do it. Any question or comments?
Okay, any comments?
No?
So yeah, please consider reviewing the document and perhaps making comments.
Okay, back to work. Thanks.
Okay, thank you. Okay, so then the next presentation will be given by myself on the topic of transmission of SHIC compress packets over 15.4 networks. Okay, so hello again. I'm going to present the last update of this draft entitled Transmission of SHIC compress packets over IEEE 802.15.4 networks. My co-authors are Anna Miraburo and Flavian Mulek from Aclio. Next, please. So first of all, a couple of slides as a reminder for the motivation and the context for this document. As this working group knows well, RFC 6282 has been the basis for header compression in 6LoWPAN and also in 6LoW. With this RFC, it's possible to compress an IPv6 UDP header, 48-byte IPv6 UDP header, down to 7 bytes in the best case with global addresses. However, it is possible to apply a more recent specification, which is called CHIC, which is the main product of the LP1 working group, which contains a header compression mechanism. And with CHIC, it is possible to compress the same 48-byte IPv6 UDP header down to just something like, for example, 1 byte. So CHIC uses static context, and it's based on a priori knowledge of the header field values for the packets that will be transmitted. So that's why it can be a little bit more aggressive in the header compression that it performs. So then, if we also consider an application layer protocol like CoAP, there is no 6LoWPAN style header compression defined for CoAP. However, there is a specification on how we can compress CoAP headers with CHIC, that's RFC 8824. The CoAP headers are of variable size, so here we are considering 2 possible cases. A corresponds to no header options. Then there is the header size is 4 bytes, and B corresponds to table 6 RFC 8824, where there's an example with a CoAP header size of 16 bytes. By using CHIC, it is possible to compress those headers in both cases down to just something like, for example, 1 byte. So overall, summarizing, if we consider the joint IPv6 UDP CoAP header, without any compression, it would have a size of 52 or 64 bytes, respectively. With 6LoWPAN, we can compress that down to 11 or 23 bytes. However, with CHIC, it is possible to compress that same joint header down to just 2 bytes. So theoretically, it would be possible to achieve significant improvements. For example, a battery lifetime improvement for a node that's using 15.4 as the read interface by a factor which, as you will see later, might be even greater than 2 in some cases. Although caveat here is that, well, actual improvement will be lower since it will depend on the specific device hardware features like the sleep current consumption, MAC adaptation or application layer settings, the payload size, network topology, and so on. Next, please. So to illustrate this possible lifetime improvement factor, the figure here shows some results. On the vertical axis, it shows the maximum battery lifetime improvement factor. On the horizontal axis, it's the CoAP payload size. And here we are assuming that we're using short MAC addresses, intra-PAN communication regarding the 15.4 settings. And the idea is that this is for a battery-operated sensor that periodically transmits one message over 15.4. So we consider 2 different scenarios, the star topology, meaning one-hop communication, and multi-hop, but with mesh under. And also we are considering the 2 possible cases for the CoAP header. So as you can see, the improvement factor decreases with the CoAP payload size, although it remains quite significant, at least for some range of payload sizes. And nevertheless, well, we need to keep in mind that in practice, the actual improvement will be somewhat lower. Next, please. So on the status of the draft, this draft was adopted in January. Version 00 as working group document had the same content as the last corresponding individual draft. And today I'm presenting version 01, which includes several significant additions. You will see that this presentation is longer than in previous meetings. And also we have a new co-author who's Flavian Mulek. Welcome on board and thanks for contributing. Next, please. So this is a div of the table of contents in 01 compared with the previous version of the document. As you can see, there are several new sections or subsections, and actually 2 of them are quite substantive in terms of the functionality that is being enabled now. So the first one is what we call the pointer-based route over approach for multi-hop communication. And the second one is enabling what we call a transition protocol stack, which, by the way, we'll present on the next slide. Next, please. So now we're going to see the different updates in 01 by the same order in which they appear in the document. So the first update is in section 3.1 protocol stack, where precisely there's this new component I was mentioning, the transition protocol stack. So on the left, we can see the two leftmost protocol stacks are the ones that we had been presenting in or including in the document in the previous versions. The leftmost one is the traditional 6LoWPAN based protocol stack. The one in the middle is the initial one or the main one that we had been considering in this document, where the goal is to use SHIC for header compression instead of 6LoWPAN for header compression. But now in 01, we have added a third possible protocol stack that would be also a result for this document, which is the one on the right, which we call the transition protocol stack, where the idea is that 6LoWPAN would be used to compress IPv6 headers, but then we would use SHIC to compress UDP and COAP headers. So the idea here is to ease a transition from the existing 6LoWPAN implementations to introduce the support for SHIC. So the idea is to allow reusing the existing 6LoWPAN implementation code, but then also benefit from using SHIC for the end-to-end protocols like UDP and COAP. Any comments? Okay, next, please. So section 3.3 describes the multi-hop communication approaches that we are considering. Previously in 00, we had 3 approaches. Now we have one more that we have added in 01. So as a reminder, the first one is what we call the straightforward route over approach. This is the one where all nodes, including routers, must store all the rules in use in the network. So this is suitable mostly for small, stable networks, because otherwise, this approach is not very scalable with network size. So then, to try to solve a little bit the problem of scalability, we introduced in the previous version the tunneled ripple-based route over approach, by which only the endpoints are the ones that must store the rules, and only for the communications they are involved in as endpoints. So this is based on ripple non-storing mode, IPv6 in IPv6 tunnels, and then this is compressed by using RFC 8138. However, here in 01, we are introducing another approach for route over, which is called pointer-based route over approach. So here, as in the previous one, intermediate nodes like routers do not have to store the compression rules. And however, the advantage here is that the pointer-based approach doesn't require those routing artifacts from ripple non-storing mode, the tunnels, and 8138. Here, the solution is based on just adding some additional field that you will see later after the SHIC dispatch, which is a pointer, and this will allow intermediate nodes to determine, to reconstruct which is the IPv6 destination address whenever they receive a packet, so that they can make routing decisions and send the packet to the next hop. So later I will describe a bit better what this is about. And the last approach is the mesh under approach, where also only the endpoints are the ones that must store the rules for communication, only the communications they are involved in. Next, please. So we have also some updates in the tunneled ripple-based route over approach. So please, we need to introduce a little bit of context. Yes, Laurent? You were in the queue for a few seconds. Maybe you will speak later. Okay, I guess you will speak later. So on the tunneled ripple-based route over approach. So the overview is, we assume ripple non-storing mode is used here. then packets sent by one 6LN are tunneled first up to the root, and then if the final destination is not a 6LN, packets are tunneled downward from the root. And then we use 8138 to compress the routing artifacts. Then RFC 9008 describes what is needed to allow downward or upward traffic within a Ripple network. And for downward, we need a tunnel, except when the root itself is the packet source, and the tunnel terminates at the last routing aware device. So it could be the 6LN if it is a routing aware leaf, or it would be the last 6LR if the 6LN is actually routing unaware. For upward traffic, then there would be IPv6 in IPv6 also initiated by the first 6LR if the 6LN is routing unaware. And in theory, the tunnel is a may from the 6LN if the 6LN is routing aware. Next, please. However, recall that in this document, we update 9008 because here we need to transform the may into a must so that a 6LN transmitting a SHIC compressed IPv6 packet upwards, then the packet must be tunneled, and that's regardless of the final destination. But then here we have the problem, which is what we try to address in 01, which is, okay, when the 6LN is routing unaware, what happens with the first or the last hop for upward or downward transmission? Because we also want that transmission to be efficient. We also want to have some way to compress the IPv6 or the additional headers. So the solution that we have considered for 01 is that for upward communication, the first 6LR should be provided with the SHIC rules for the packets that would be sent by that 6LN. And the same would happen for the downward. In this case, it's the last 6LR that should be provided with the SHIC rules for the packets that would be sent to the last node, which is the 6LN, which would be routing unaware. So perhaps this is maybe not the most nice or the best possible ideal solution in the world, because then it reduces a little bit the dynamics or the flexibility that we can have in the network. Here, this is a wireless network, which might be quite dynamic. So to really apply something like this, we need to know in advance somehow which will be the neighbors that the first 6LR will have or the last 6LR will have. So yeah, maybe there's a little bit less of flexibility, but on the other hand, this would allow to be also efficient in the transmission in that last or first hop. So, okay, if there are no comments, then next, please. So yeah, on the other approach that we are considering for route over, which is called pointer-based route over approach. Here, the idea is to provide some alternative to the tunnel ripple-based approach that I was just presenting. Here, the idea is that in the 15.4 frame payload, after the SHIC dispatch, we would place a SHIC pointer. And the pointer will indicate the location and the length of the destination address residue in the SHIC header, the SHIC compressed packet, okay? So here the idea is, okay, the intermediate nodes, we don't want them to store the rules. We want to keep them simple from that point of view. So then whenever they receive an incoming packet which has been SHIC compressed, then by using this technique, they would still be able to recompose which is the destination IPv6 address, because the prefix is known, and they only need to find which is the destination address residue after the compression. So the pointer will tell what is precisely that destination address residue, which is its location and size within the compressed SHIC packet. So here the assumption is that the destination is within the same 15.4 network, and for sending data to some external node, we would need to think about some additional solution. However, this is lightweight. You will see later the frame format for this. It's actually more lightweight than the tunnel ripple-based approach. It is also compatible with ripple storing mode or with other routing protocols. And again, nodes are relieved. They don't need to store the rules for all communicating endpoints. Actually, they don't need to store any rules if they're not involved themselves as endpoints. So, any comment so far? Okay, later I will present the frame format for this approach. So next, please. So as you can see now, we have like different communication modes enabled by using different possible techniques. Let's see whether as we progress, we identify that maybe we could get rid of some of them or combine them or what we do. But we've added a summary to clarify a little bit the different approaches that we have. So this is also added in the document. We can transmit at one hop, or we can have multi-hop communication. And here on the table, there's the additional artifacts that we need to support them. So for one hop communication, we only need the SHIC dispatch. For mesh under, it's the SHIC dispatch plus the mesh headers. For route over, then we have the two approaches, right? The tunnel-based ripple non-storing mode, where we need the tunnels, the different 6LO RH fields, and also the SHIC dispatch. And then we have the last one, the pointer-based approach on the rightmost column, where it supports ripple storing or other routing protocols. And here we just need the SHIC dispatch and also the pointer. Next, please. So section 4 describes the frame formats that are used by these different approaches. So what I'm going to present is just the new frame formats that have been added in 01. So first, we have one frame format added in folder 2, which focuses on the tunnel ripple-based route over. This is for one case that we had been missing before in 00, which is when we have downward transmission and the source is actually the ripple route itself. In this case, there is no tunnel. It's kind of an exception. So the format is the one you can see on the slide. What you can see is actually the 15.4 frame payload, which starts with a page switch indicating we are in page 1 to allow compression by means of 8138. Then the corresponding source routing header and the ripple information fields compressed with 6LO RH. And then there would be the SHIC dispatch, and after that, the SHIC compressed packet. Next, please. So folder 3 describes the frame format for the pointer-based route over approach, the new one that I was introducing before. So on the figure on top, you can see the frame payload of the 15.4 frame. The first field would be the SHIC dispatch, and the novelty here is the SHIC pointer, which comes after the SHIC dispatch. Again, the pointer will tell where in the compressed SHIC header there will be the destination address residue and which is the size of that, so that any node can find and reconstruct the full IPv6 destination address even without knowing the rules. Then after the SHIC pointer, there would be the SHIC compress packet, and then if needed, padding. So about the SHIC pointer, currently it has the format that you can see at the bottom of the slide. The first bit of that is a P bit, which indicates whether the next fields would be present or not. And the second field is the bit pointer, which indicates which is the starting position of the IPv6 destination address residue in the SHIC compress header. After that, currently there's a 0. However, perhaps this could be used for future functionality. And the last field is this address length. Actually, it corresponds to the length of the IPv6 destination address residue. So this is the format that we are considering so far. And perhaps we might discuss what to do in future versions, because, for example, another approach could be to define a second SHIC dispatch just to tell that what comes next is a SHIC pointer. So perhaps in that case, we might save at least the P bit. Let's see. Okay, that's one option, one idea. Any comments? Okay, so next, please. Finally, just for completeness, we have also added here in section 4, which are the frame formats to be used if we are using mesh under. So basically, we are not defining new formats here. This is just the same as those defined in RFC 4944, however, using the SHIC dispatch instead of where there would be the original dispatch with the possible IPv6 header compression at the time of 4944. So here we can see the formats when no fragmentation is needed, where at the beginning there's the mesh header followed by the SHIC dispatch in this case, or when we need fragmentation, where we have the mesh header, then followed by the fragmentation header, then followed by the SHIC dispatch. Next, please. And this is the format when no fragmentation is needed, but we use the broadcast header. Then the order is we first have the mesh header, then the broadcast header, then the SHIC dispatch. So actually, we just follow what is in RFC 4944. However, again, for completeness and clarity, explicitly describing these formats. And then when we have several headers that need to be present, we follow the same order. They need to appear in the same order as in RFC 4944. First the mesh header, then the broadcast header, then finally the fragmentation header. Next, please. So initially, I talked about enabling this transition protocol stack, where the idea is using 6LoWPAN to compress the IPv6 header, but then using SHIC to compress UDP co-op headers. So how do we want to enable this? Well, the approach we are considering is to exploit some ongoing work that's happening in the Interior Working Group to define an Internet protocol number for SHIC. So this means that there will be a way to signal in the IPv6 packet header when the payload is a SHIC packet. So as a result, in this approach, we would have, as the 15.4 frame payload, the first field would be 6282 compressed IPv6 header. Here, the NH field would be set to 0, and the next header would be actually the SHIC Internet Protocol number. This would be uncompressed. By the way, for the moment, it seems like the tentative number for SHIC here would be 145. Let's see whether that is confirmed after the whole process. And then the payload of the IPv6 packet is the SHIC compressed packet, which in this case is SHIC compressed UDP datagram, which carries a co-op data unit. So in this case, what follows is the SHIC compressed UDP co-op headers and then the co-op payload. And then finally, padding if needed. Any comment on this? Otherwise, next, please. Then we also have one subsection added in section 6, which is the one that describes how to compress the IPv6 or UDP fields. So here we focus on the UDP checksum. So in RFC 8724, which is the base SHIC specification, there is text stating that the SHIC compressor may align the UDP checksum when another layer guarantees at least equal integrity protection for the UDP payload and the pseudo header. So we are using 15.4 here. So 15.4 carries a 16-bit frame check sequence, which is computed by using the ITUT 16-bit cyclic redundancy check, CRC. So this frame check sequence has the same size as the UDP checksum. It is known that it has greater error detection capability than the UDP checksum. And even if we consider multi-hop communication, then the 15.4 CRC will be checked at each hop. So first conclusion is that it's possible to actually align the UDP checksum if we are using SHIC here. And then the other point is, okay, is there any scenario where we would not like to align the UDP checksum? So at the moment, we didn't realize of any such scenario. So what we have in 01 is that the UDP checksum must be aligned when using SHIC to compress UDP headers. So if anyone realizes of some case where you think that must is not actually suitable, please let us know. Okay. Next, please. So we've also added a short section on neighbor discovery. So not adding new functionality, but rather first explaining that there have been several neighbor discovery optimizations developed for 6LoWPAN or 6LO, such as RFC 6775 or RFC 8505 and a few related ones. So here the point is to explain that SHIC can also be used to compress 6LoWPAN neighbor discovery messages. So as of the writing at the moment, SHIC compression for ICMPv6 or ICMPv6 based protocols has not yet been specified. However, at least the IPv6 header of such packets still could be compressed, but then perhaps future specifications may define how ICMPv6 and 6LoWPAN neighbor discovery messages can be compressed by using SHIC. And in fact, there's quite an interesting thing happening, which is the LP1 working group is transforming into the SHIC working group, and it has a new charter. Actually, SHIC can be applied not only in LP1 environments, but also beyond those, as you can see precisely in this document. And the new charter for the SHIC working group includes working ICMPv6 based protocols over SHIC. So this means that if such work actually ever happens, then we would be happy from this document point of view, because then we could be a customer of such functionality. So for the SHIC working group, this is like a call to see if anyone is interested to actually develop such a work, such specifications. Next, please. So the last slide, just rather a comment on the security considerations that we have in the document, one aspect of them. There is one kind of problem. RFC 8824 states that if there is a layer 2 different from LP1 technologies as the way to transmit packets where we're using SHIC to compress COAP headers, then 8824 requires, so this is a must level requirement, requires the use of a cryptographic integrity protection mechanism to protect the SHIC headers, okay? However, we were wondering, okay, perhaps why couldn't this be actually a should? Because the point is that, for example, in 15.4, there is one mode which is no security. 15.4 also supports several security services. However, there is one mode where there is no security. So perhaps there are scenarios where security is really not so relevant. But perhaps we might still like to benefit from the SHIC improvements, also for the cases where security is really not needed. So in parallel, there is some effort, which is some document presented yesterday in the LP1 or SHIC working group, which is an RFC 8824 update effort. And this point was already presented. The idea of, okay, is it possible maybe to use the effort to update 8824 to also lower the must down to a should? So we had some reaction from Eric Winker that perhaps the AD, the security AD, would not be happy with that. However, perhaps maybe these considerations were not made at the time. So let's see whether we can actually discuss this point, and let's see whether it's possible to actually have the must or the required in 8824 reduced to should, because then we might benefit from greater performance improvement if we use SHIC in those 15.4 scenarios where there is no security actually in place. So next, please. So yeah, that was my last slide. Are there maybe any comments or questions? Yes, so Stuart is in the queue.
Hi, I just wanted to say thanks for presenting this work. This seems really good. When you talked about omitting the UDP checksum to save 16 bits, I was very supportive of that because any modern protocol really needs to have cryptographic security. And if you have cryptographic security, then you know with high confidence whether the data is being corrupted intentionally or accidentally. But then when you talk about making security optional as well, I kind of feel like those two things conflict with each other. And I feel like we can't have both. We can skip the checksum if we know we have security. But if we don't have the checksum or security, then we become very vulnerable to accidental corruption.
Yeah, perhaps there is also the point that in those networks, well, perhaps we will need to see how many 15.4 networks out there are not using security or the no security mode, because there would still even the option of having no security at the 15.4 level. But still, we have the integrity protection, not cryptographic, but integrity protection, which would suffice for eliding the UDP checksum. So I don't know if maybe that could still make sense in some scenarios. Perhaps the point would be whether there are many or not 15.4 networks out there which do not use security at layer 2. But at least from the standard point of view, it's one of the modes, actually one of the mandatory modes to be supported by an implementation.
I'm a big fan of end-to-end integrity. There was some research a while ago that most data corruption on the internet doesn't actually happen in transit. It happens due to software bugs and hardware DMA engine errors and race conditions in the routers forwarding the packets. So hop by hop integrity is a good thing, but most corruption actually happens, ironically, while the data is sitting in RAM chips waiting to be forwarded. So if we recompute the integrity or the security on forwarding, then the corrupted data just gets signed as correct. So I'd be worried about omitting end-to-end integrity checks.
Okay. Okay, thank you. So any other comment?
Thanks.
Okay. Okay, so is there maybe, sorry, is there any other business, any comment, anything else? So then this concludes the session. Thanks everyone for attending, especially for those in bad time zones at the moment. And let's continue discussing on the mailing list and hope to see you in San Francisco.